I'm going to tell you a little bit about this this space mission called New Horizons to begin. I know I spoke to the group well before the flyby, but I'm going to give you a bit of a refresher, and also that ought to help people who didn't see the other presentation. But most of what I'm going to tell you about are going to be results and a lot of eye candy from the flyby, both about Pluto and about its moons. So just to remind you, we launched New Horizons almost exactly 10 years ago. In fact, it'll be 10 years to the day next week. We launched on the 19th of January 2006, flew a trajectory directly to Jupiter, and arrived at Jupiter very quickly, just 13 months later. We were the fastest mission ever to reach Jupiter, and used Jupiter for gravity assist to go on across the big expanse of the middle of our solar system to reach Pluto last summer on July the 14th. And then as the red trajectory in this cartoon shows, we are now out in the Kuiper belt, and we expect to do a flyby of an ancient Kuiper belt object, if NASA approves that, in the coming years. In fact, in 2019, and I'll have more to say about that at the very end. You may have heard that the flyby was very popular. We worked very hard to engage the public. We had over 2,000 people show up at our mission control. This is a nice picture of part of that crowd at the moment of closest approach. And on this next slide, I just wanted to say a little bit about the public outreach. This is the first time that anyone had flown a spacecraft to a brand new planet since Voyager 2 was at Neptune in 1989. And for about half the people on Earth, they'd never seen anything like this. They were born since that flyby, or they were too young to remember it. We made it on the front page above the fold of 450-something newspapers the next morning, setting a record. We had over 1 billion web hits on the day of the flyby, setting a record for NASA. And there were lots of other things. You can see we got the Google Doodle, which I thought was really cool. And we were on the covers of many, many magazines. In fact, I'll tell a funny story about that. My next-door neighbor emailed me during the early parts of the flyby, and I was at Mission Control the entire summer. I lived in Maryland, where our Mission Control is, and he wrote me saying, "Alan, we take 6 magazines at our house. 5 of them have arrived, and you or your mission is on the cover of every one of them." He said, "Now the 6th magazine is Cosmo, and if you're on the cover of that, I'm jumping off my roof." So I saved his life. We were not on the cover of Cosmopolitan, but we were really happy with the public response to the flyby. I think it really shows how much regular people, not people like yourselves who have an interest in space and astronomy, but regular people who really like space exploration when you do something brand new like that. And, really was a great lesson learned for NASA as well. So I'll go on and tell you more about this mission. As some of you know, the scientific community has wanted to have a mission to Pluto for a long time. And there's a list on this chart of various Pluto missions that never made it off the drawing board for one reason or another. But I show this to show that the scientific community worked time and again from 1990 on 6 different versions of how we might do Pluto missions, and every time one was canceled or ran into problems, the community persisted, really wanted to do this exploration. Ultimately, New Horizons is the mission that we flew, and that's what I'll be telling you more about. You might wonder why there was so much persistence. Part of the story is that although Pluto's very far away, and we're very limited by that distance in getting to know Pluto well without sending a space mission, the things that we could determine from ground-based telescopes and from space-based telescopes orbiting the Earth were really tantalizing. and got the U.S. military science community very excited. A few of them are here. The graph along the top is an infrared spectrum of Pluto showing that its surface has 3 different volatile ices, nitrogen, carbon monoxide, and methane. And that makes for a very complex interplay and a very complex climatology on Pluto. So that was really enticing. We discovered that Pluto has an atmosphere. We discovered it through a stellar occultation made in the late 1980s. We discovered that Pluto, although it's icy on the outside, is primarily made of rock, and that was a real surprise. People did not expect a rocky planet on the outer edge of the solar system. By determining Pluto's radius through the stellar occultation technique and measuring its mass using Kepler's laws and the orbits of its satellites, we could get the density, and that's what told us that it's about 70% rock. We also learned that Pluto and its big moon, Charon, form a binary, and there was a lot of interest in going to see a binary planet. That's a type that we think is probably common in the universe, and yet all of our exploration out to Neptune had not given us an opportunity to explore a binary. So all of this was very important because NASA gets lots of good proposals for missions, many times more proposals than it can possibly afford to fly, and in order to get funded, you really have to rise to the top. And Pluto was near the top of the list many times, but what really took it over the top was the discovery of the Kuiper Belt. And I'll show this video. And I just realized it's got sounds, which we can't avoid. So I'll have to speak over that. But these are Kuiper Belt objects being discovered across the 1990s and into the 2000s. The larger ones are shown with bigger dots. And you'll see this, we're looking down on the solar system, you'll see it pivot, and then you can see from the edge that it's quite a thick disk of objects that ring our solar system. Truly amazing. Now, the discovery of the Kuiper Belt taught us that the solar system had a different architecture than we previously understood. Not just the inner planets and the giant planets, but a third zone beyond the giant planets. In fact, we used to call the giant planets the outer planets. Now we typically call them the middle solar system, or just the giant planets. This third zone had never been explored, and one of the things we discovered about it, I think the most interesting thing, is not that it existed and that it's home to the short period comets, but that it's also home to quite a number of small planets that give Pluto context. Here you see some of their names, like Eris and Makemake and Haumea and Sedna. And when we realized as a scientific community in the late 90s and very early 2000s, this fact that the Kuiper Belt is littered with small planets, that really rocketed the priority to do a Pluto mission from the A-list to the top of the A-list, to make it number one. And in fact, the National Academy of Sciences, which sets priorities for NASA planetary missions, ranked this mission number one for a new start in the 2000s because of the discovery of the Kuiper Belt and the realization that by flying to Pluto, you'd not only better understand all the physics that I talked about and the Pluto system very well, but also that it would be our first chance to explore this third zone of the solar system. So NASA conducted a competition, and we proposed, and other teams proposed, and we were fortunate to win that competition, the New Horizons team. There you see in the lower right the cover to our proposal, which we wrote back in 2001, and it was really the end result of this proposal and that decadal survey that made this mission possible. The primary objectives that we set were threefold. First, to map Pluto and its big moon Charon. By the way, at that time, that was the only moon of Pluto that was known. To map the surfaces of those two bodies, to map their surface compositions, and to characterize Pluto's atmosphere and understand its escape rate. Now, there were many, many other objectives, but these were the three that got top billing. And some of the others have to do with searching for more satellites, searching for rings, understanding Pluto's atmosphere, many other things. One of them is illustrated here, and that is that we also promised to do very high-resolution imaging compared to any other first mission. There on the right, you see that picture, blow-up of New York City. And even if you're not familiar with New York City, this is the resolution that New Horizons would obtain if it were to fly by the Earth and fly over North America at the same altitude that it actually flew over Pluto. So if you look in the middle there, you can see Manhattan Island with the Hudson on the left and the East River on the right, and you can see the green triangle, which is Central Park. And those markings you see in Central Park are ponds in Central Park. If you look carefully along the west side of Manhattan, you can just barely see ships, not ships, but the wharfs for ships on the Hudson. And this just gives you an idea of how detailed the imagery that we plan to take at the flyby would be. And in fact, all of that worked just spectacularly. So we were very happy with it. New Horizons, which you see here in the upper right, with people around it for scale, it's a pretty small spacecraft. It was intentionally built to be small, primarily so that we could launch it very fast. We bought a very large rocket, we put a small spacecraft on top, and that delivered very high speed. The spacecraft carries 7 scientific instruments. They are together very highly miniaturized. They weigh, all 7 combined weigh less than just the camera on the Cassini Saturn orbiter. They don't take much power. We had some real breakthroughs in the technology that allowed us to reduce the power requirements. All 7 instruments combined, if you run them all at once, draw just 28 watts, which in the U.S. is about a half a light bulb, a standard light bulb. And they carry a very impressive set of capabilities. I'll just very briefly go over what the different instruments do. Ralph is our color camera and our composition mapping spectrometer. It's also our main geologic mapper. You can see its telescope sticking out front of it. Alice, which sits just above it, is an ultraviolet spectrometer, which is designed to determine the structure and composition of Pluto's atmosphere. Rex up top is radio science, and it's another atmospheric instrument. It allows us to determine the temperature and pressure in Pluto's atmosphere. It also measures the temperature of Pluto's surface. SWAP and Pepsi actually sample the gases coming off Pluto's atmosphere with charged particle spectrometers. And LORRI is our long focal length camera. It's basically a high-tech Celestron 8 with a CCD in the back. It doesn't have color capability like Ralph, but it's got a much longer focal length, so it could make images with resolutions as high as 70 meters per pixel, like that image of New York on Pluto. And then we flew a dust impact detector built by students here in Colorado at the University of Colorado. And actually, that's a very important instrument for studies in the Kuiper Belt because we know that the Kuiper Belt is dusty. It's also the very first time a student-built instrument was ever carried on a NASA planetary mission, and I'm very proud of that because that worked out so well that a lot of planetary missions do it now, and students get a lot of opportunities early in their career to get involved in planetary missions. As I said, we launched 10 years ago next week. These are pictures from the launch. The launch vehicle is an Atlas V, and we went directly to Jupiter. This is the cover of Science magazine back in 2007 after our Jupiter flyby with images of Jupiter and its volcanic moon Io made by New Horizons. We studied Jupiter's atmosphere, studied its satellites, its magnetosphere, its aurora, many aspects of the Jupiter system, but we were, after all, the 8th mission to reach Jupiter. Our primary purpose at Jupiter wasn't the science. It was really to make that gravity assist, and to do that we had to navigate to a very specific aim point at Jupiter so that Jupiter could bend our trajectory and accelerate it to the one place we wanted to go, which is where Pluto would be in the middle of July in 2015. But we also used the flyby at Jupiter to test all the onboard systems, because Jupiter is the only thing we passed along the way. So this also became a dress rehearsal in some respects for the Pluto flyby. Now I'll jump ahead eight years and talk about the flyby itself, and tell you a few things that you may not know. One thing that very few people appreciate is that the actual flyby operations take 2 years, and we're still in the middle of them. And I know that many of you are thinking, well, it went by Pluto back in July, what's going on? Well, we spent 6 months flying up to Pluto and taking data, both to navigate to the right place in the solar system, but also we took data for scientific purposes, to search for new satellites, to understand new things about Pluto's environment and Pluto itself. Everything reached its peak on the 14th of July, and we continued to take data after we left, looking back at Pluto. I'll show you some data from that phase. But we specifically designed New Horizons to take an enormous quantity of data. In fact, let me make a comparison. When the first mission went to Mars 50 years before in 1965, they filled their tape recorders, and if you calculate the ratio of the data that we took to the data that they took on that first flyby of Mars, New Horizons captured about 5,000 times as much data. And because we filled our memory banks with so much data, it takes a long time to ship it all home. We're still doing that. In fact, here it is early 2016, and we're not yet even halfway through the data transmission. It will continue through late October or early November this year. We see new images and spectra and other data types every week, and you should too. If you're following this on the NASA websites or other places, you probably know that we're releasing new imagery and making new discoveries all the time. So I want to tell you a couple of things that are unique about this flyby. One is that because Pluto, like the planet Uranus, is tipped on its side, we came at it sort of like flying at a bullseye. There you see the red trajectory line again. The spacecraft is coming from the lower right to the upper left. And you can see the Pluto system in the orbits of its satellites, how steeply it was inclined to the trajectory. And that made a challenge for our flyby design, because we basically passed by everything at closest approach simultaneously. If the system had been arranged differently geometrically, we would have been able to go by one satellite and then the next and the next. But because Pluto's tipped on its side, that wasn't possible. So it made it some very interesting choreography to do all six objects in the system all at once. The other thing is that we had to fly very precisely in order to put the spacecraft behind Pluto in its shadow to do some of the atmospheric experiments. And we also wanted to repeat those experiments by flying through Charon's shadow in order to search for an atmosphere around Charon. And that required that we hit a very tight window in space at Pluto. In fact, about 100 kilometers on a side. And we had to arrive at a very precise time. We had to arrive after 9.5 years within plus or minus less than 10 minutes. And we did all that. In fact, we actually arrived about 90 seconds early, but very much within that 10-minute window. And we were right in the middle of the box in terms of the aim point, so we were able to conduct these experiments in the shadows of Pluto and Charon. I'll show you results from that in just a minute. So let me start with this nice kind of family portrait made by New Horizons. By the way, I'm going to be using the names that we on the New Horizons team use for surface features. None of them are formalized yet, so they're all what we call informal names, but it sure makes it a lot easier to have names for things than to just use latitudes and longitudes or numbers. Nobody can remember all that. Anyway, here's Pluto in the lower right, and then its big satellite Charon, about half Pluto's size, and beyond that, the two small satellites that were discovered by the Hubble Space Telescope, by our team using the Hubble Space Telescope back in 2005. Those two are called Nix and Hydra, and I'll show you much better imagery in just a moment. There are still two more satellites that are not in this particular montage, called Kerberos and Styx, and I'll have imagery of them as well. But I like this single shot that shows all four. It shows them to scale. So here are the four small satellites of Pluto. Along the top, they're shown to the same scale and in order as you move outward from the binary. Styx is closest to the binary. Then there's Nix, then there's Kerberos, and then Hydra is the farthest out. And you can see, and we don't understand why. I'm going to tell you a lot of things we don't understand. We're just getting to know the system. But for some reason, they alternate between small and big as we move outward. There are two pairs. Styx and Nix are a small one and a big one, and Kerberos and Hydra are just the same. And the sizes of Styx and Kerberos are not very different. The sizes of Nix and Hydra are not very different. And whether that's chance or telling us something important about how the small satellites formed or evolved, we're not sure. We don't yet have compositional spectroscopy. We do have a little bit of color data now, and those are shown in the lower two figures here. One of the things that's puzzling us right now is that all four of these are very highly reflective, with reflectivities of 70% or so, which suggests that their surfaces are made of very clean ice. This is in contrast to Pluto's big moon Charon, which is about half as reflective. We're looking forward to having compositional spectroscopy to see if, in fact, ices are on their surface, but we don't have that yet. Here's a close-up of Nix. This is the one that we flew closest to of the four small ones. And you can see from these images that there are a variety of different surface features. There are craters, there are ridges, there are what look like stress fractures that are linear. I think you can see my arrow. I hope you can, and there's an example of one. There are parallel features like that all over this image. We're just getting to the analysis of these images. One thing that strikes us about the small satellites is that it looks like at least two, and maybe all four, are the result of mergers of two or more bodies. You can see it here as well. And that suggests that Pluto once had more satellites, that they have found each other and gently collided or merged into the current satellite system. I think that's pretty unexpected. And this is also an unexpected result. Here I'm showing the rotation rates of the four small ones. Now, nothing is to scale here, so Pluto and Charon are actually very large compared to the four small ones. The only point this graphic really makes is that the four little ones rotate very quickly compared to their orbital periods. And this was not expected. It should be that over time, they should have damped into a synchronous rotation state, but they haven't. And we don't know if that means that they are young, or if it means that there's something exciting their rotation states or what, but in all the other satellite systems across the solar system, we have never found a situation like this, where the small satellites close to a planet spin quickly. In fact, Hydra, which is the outermost one, spins so fast that it makes about 90 turns on its own axis before it makes one circuit around Pluto. All right, let's move on. Now I'm going to talk about the big satellite Charon, which, frankly, if it was orbiting in the Kuiper belt by itself, we would count it among the small planets of the Kuiper belt. It's 1,200 kilometers across, 1,214 to be more precise. It has a complex history geologically. We can see that. I'll show you a better image in just a moment, and I'll talk a little bit about that. But I want to tell you that we have some very interesting other results. In the upper right is a little graph that's just reminding me to tell you that we looked for an atmosphere around Charon, and we can now definitively say there is none. Even down to pressures of 1/1 billionth of the pressure in the room where you are and the room where I am, we can prove it because we don't see any signature of the atmosphere when we do the occultation experiments that we did. Looking at Charon's surface, we find some interesting things. One is that some craters, like the green one in that middle plot, that's not truly green, it's just artificially colored green, show us that ammonia ices lie below the water ice covering on Charon, and that craters excavate that ammonia onto the surface of Charon. We also, in that lower right image, you can see near the terminator where the lighting is favorable, that there are whole fields of not craters but pits on Charon's surface that may be the result of outgassing from the interior. We're not sure, but it's quite surprising. It's unlike anything seen elsewhere across the solar system, and we're scratching our heads about it. As to Charon's geology, this image that I'm showing now shows you that Charon's had a pretty rough past. There are a lot of craters. It's pretty beat up. There's a very large extensional tectonic belt that runs basically across its equator from left to right here. It runs about 1,500 kilometers wide. It's much larger than anything else that we've seen on a solid planetary surface. It's much larger than the Grand Canyon. It's much larger than Valles Marineris on Mars. It's also deeper. But beyond the tectonics, we did not expect to find this red stain on the North Pole of Charon. We're not sure how it got there. One theory is that it may be the result of atmospheric spillover from Pluto onto Charon, and that these are the residues of that spillover. If that's true, there should be a similar red stain in the south, but the south pole of Pluto is not visible to New Horizons. It's in polar shadow right now, just like Antarctica is on Earth. So we'll have to wait about 25 years until it comes out of that and into the sunlight, and by then, ground-based telescopes, space-based telescopes should be good enough to see big features on the surface of Charon, so we can test that theory. If you look carefully in the northern hemisphere, you'll see many more craters and rougher terrains than in the south. That's because it looks like the southern terrains have been flooded with some sort of a icy slurry that has since frozen out and erased a lot of the old geology. Also, if you look at the craters on Charon's surface, you'll note that many have bright ejecta blankets, but many others have dark ejecta blankets. And that could be telling us that Charon's crust varies in composition from place to place, that there are two types of crustal materials, the darker and the brighter. We're really not sure, but like a lot of things in the Pluto system, the data is fresh from the spacecraft, and we have not had time to really do the hard science, only to just do the quick look analyses. I'm going to move on now and talk about Pluto for the remainder of the talk. This slide shows you a series of images of Pluto made in the final days before closest approach, as we were coming in from millions of miles away. And the images in the bottom, down at the 6 o'clock position, are of the approach hemisphere, where we flew over and have very detailed imagery that I'll be showing you. But I put this in the presentation so you know a couple of things. One, we mapped all of Pluto at this kind of resolution, and we can see that Pluto's opposite hemisphere is very different than the approach hemisphere. You can see that too. You can also see that the large dark feature in the south, it's actually in the equatorial region of the approach hemisphere down at 6 o'clock, stretches almost halfway around the planet. And you can only see that by looking at the other images here. I have to tell you, these images are really tantalizing. They're the best look we're going to get at the far side of Pluto for a very long time. I have high-resolution imagery of the close approach hemisphere, but nothing better than this for the other terrains. Now, this is still 100 pixels across and much better than this. We had a Pluto before the New Horizons flyby. and just switching between the two, you can see what a dramatic improvement we've made. This image was made by the Hubble Space Telescope, and it still hasn't been bested until we got a spacecraft to Pluto. But with new telescopes that will be coming online in the 2020s, primarily gigantic 30-meter class telescopes here on the Earth that use adaptive optics, we expect to be able to image Pluto almost as well as the images of the far side here. And that'll be very important because we think that Pluto has complex seasonal changes and it snows, move around on the surface. We have other reasons to believe that Pluto changes with time, and it'll be fascinating to be able to re-image Pluto in 10 or 20 years like this from the ground and compare the images to what Pluto looked like in 2015. So let me move on now and tell you more about Pluto. Pluto itself, I'm going to leave the satellite system after I talk about this one last slide, which just shows the binary in stark contrast to one another. You can see how different Charon looks than Pluto. It's about half Pluto's size and very similar in internal composition and density. It's also a little bit more than half made of rock, about half rock and half ice. Pluto's about 70% rock, as I said before, only about a third ice, but Pluto's surface is covered in these exotic ices, the nitrogen, the methane, and the carbon monoxide, and that makes a very different surface appearance. And as we've also discovered, Pluto is geologically alive to this day, and all the terrains on Charon's surface appear to be old. It looks like Charon, the geologic engine in Charon ran out a long time ago, and it's been weathered by space exposure, but hasn't been evolving very much, as Pluto has, for the last 4 billion years. It's really puzzling why this binary is so dichotomous, why it's so different. These two objects have been together for billions of years in the same thermal environment, the same radiation environment, the same impact environment, and they don't look anything like one another. And I think that's telling us that when we fly missions to other planets in the Kuiper Belt, we should expect to see very different objects from either Pluto or Charon. We'll see when we get there, but that's certainly a tantalizing hint. Now here's a nice image of Pluto made on the day of closest approach with roughly 2-kilometer pixels. And there you see the scale bar. One of the things that we can determine from this image is Pluto's diameter, which was uncertain before the flyby. It turns out it's larger than was expected by several tens of kilometers. And it is now known that Pluto is the largest of these small planets in the Kuiper Belt. For a while, we thought it might be smaller than a rival object called Eris, but now that we have Pluto's diameter very precisely, we know that it's actually a few percent bigger than Eris, and it's the king of the Kuiper Belt, as some people say. But looking at its surface surprised us very much. It's a lot more complex geologically than you might expect. Of course, the front side, or the encounter hemisphere, is dominated by this big heart-shaped feature, which we call Tombaugh Regio, after Clyde Tombaugh, Pluto's discoverer. It's a gigantic ice field. From north to south, it runs over 1,000 kilometers. In the United States, that would be the size of the state of Texas, the largest of the 50 U.S. states. But we see lots of other interesting terrains as well. And I'm going to show you close-ups in the next few slides of some of those places. You can see craters, all kinds of craters that we use to age date the surface. We can see big tectonic faults, like these that I'm showing with my arrow to the west of Tombaugh Regio. There's a big rift system that runs north-south along the northwest margin of Tombaugh Regio. We have this big expanse here. It's very dark, looks like a lunar mare, as a matter of fact. It's icy. In fact, this is what we think Pluto looks like under that bright volatile veneer. Is this dark material. In fact, we see it at the bottoms of craters and other terrains. So all the bright material is just the cover to the book, if you will. Pluto itself is actually very dark, we believe. there are other kinds of interesting terrains I'll speak to as well, but first, I want to move on because I've got better graphics to show you. This is a close-up of that big ice field, the western side of the heart, which we call Sputnik Planum, after the first satellite that ever went into space, Sputnik. And as I said, it's about 1,000 kilometers long. It's ringed on every side by mountains that tower 4 or 5 kilometers above the plain. And the plain itself appears to be glacial. And I will show you evidence of that in just a minute. But I thought you would enjoy seeing the color variations on Pluto's surface. And this is a color stretched image that brings those color variations out very nicely. As soon as we started returning high-resolution images like the black and white one here, we discovered that Pluto is littered with mountains. Some come in ranges, like in the lower right. Some of those ranges even have snow caps, as you can see. And those mountains are quite tall, as I said, 3 to 5 kilometers, depending upon where you look. And we had some bets inside the science team about whether we'd find mountains or not, because the materials that we can see on Pluto's surface, like methane and nitrogen, are very weak. You can't construct big, steep mountains out of them because they would slump under their own weight. They have the viscosity, roughly the viscosity of something like toothpaste, and you just can't build things thousands of feet high, thousands of meters high, in fact, out of that. So we knew that if images return pictures of scenes like this, that it would mean that the ices we see on the surface are only a thin veneer, and that there's something stronger that makes those mountain ranges. We hypothesized that that's water ice because it's the most common construction material in the outer solar system. In fact, we've now been able to get compositional spectroscopy down, and this map of Pluto shows water ice in blue wherever it occurs, and all the mountain ranges appear to be showing us evidence of water ice. So we're pretty sure we're right about that. We're pretty sure we're right that the crust of Pluto is made of water and that the volatiles are just a thin layer on top. I want to point out one particular set of mountains that are here in the northwest of Sputnik Planum. And they're shown here topographically, with red being very high and green being middle and blue being lower terrains. And if you look at those mountains, they are not aligned in ranges. They are chaotic. They look like these big blocks, which we know now are made of water, and which in some cases are tens of kilometers long and several kilometers high. As I said, they look chaotic. And one thing that we know is that water ice is buoyant in nitrogen ice. So we believe these water ice mountains are actually floating in a sea of nitrogen. The nitrogen being the smooth material. It's smooth because it can't retain topography, as I was just speaking to. But over here in the northwest, we see these mountains, and we know they're water ice, and we know that water is buoyant in nitrogen. And really, this is a spectacularly interesting place to study for the geologists. So looking forward to learning a lot more about this region on Pluto. In the plain itself, down in Sputnik Planum, and if you look in the upper right, I failed to say, I show you on each slide where on Pluto we're looking with a little green box. When we look in high resolution in Sputnik Planum, we see this network of cells. They're not alive, they're geologic cells, or some people call them ovoids, that appear to be they appear to be convection cells in the ice caused by a thermal gradient from the bottom of the ice to the top that causes it to overturn, much like a much slower version of a roving boil in a cup of coffee or tea. But it's happening in solid state here. We've made mathematical models of how this works, and it seems to produce the right kinds of features, but how Pluto can be generating the heat to do that 4 billion years after its formation is really a mystery. We notice that on Sputnik Planum, everywhere we look, we see this kind of cellular pattern, but we do not see craters. In fact, Sputnik Planum has a surface area of about 1 million square kilometers, and we have not yet found a single crater of any size, even down to resolutions of just hundreds of meters. And this means that Sputnik Planum is very young. In fact, the geophysicists on our team can use the lack of craters to compute a maximum age of the plane, and they find it's 10 million years, and it may be much younger. So this overturning process is erasing old geology and creating new features and erasing craters that must form there very, very efficiently. How Pluto is powered, we don't understand. When we look in the northern reaches of Sputnik, we see flow lines around obstacles like these mountains, or some people call them islands, sticking up in the nitrogen. We didn't expect this either. And in fact, we started to bring glaciologists onto the team because nothing like this has been seen anywhere else in the solar system, and we didn't have the right kinds of geological expertise on our team at the time of the flyby to really understand what's going on here. One of the things that's been discovered, shown here in the mountains to the east of where we were just looking, we can actually see chutes where material has spilled out of the mountains and down into Sputnik Planum, filling it up. And we can see the flow lines in that flow, and we can age date this as well. And so this very large flow, tens of kilometers across, has occurred yesterday geologically. It may have been in the last million years, maybe even less. And so it shows that Pluto's surface is pretty active. When we look at other terrains, like these way off to the northwest, we see craters that are being buried in snows that are probably falling in Pluto's atmosphere at other parts of its orbit or climate cycle. But we also see, and I hope you can see this on your projector, these squiggly lines that are interconnected up here in the upper right. They form what the geologists call a dendritic network that could have been caused by liquids that once flowed on Pluto's surface and carved these channels. They look a lot like just those kind of channels on Mars. Now, you can't have liquids on Pluto's surface today. The pressure in the atmosphere is too low. So if, in fact, these were caused by liquids in some past era, it means that Pluto once had a big, bulky atmosphere, perhaps bulkier than Mars's, maybe even rivaling Earth's. It'll take more work to determine if that's really the case, but it's sure is a interesting possibility, and something, once again, was not predicted. These terrains are also very unusual. They run hundreds of kilometers long, and they are bladed mountains, where the individual blades are a few hundred meters high, and they're organized in parallel to one another over very large scales. No terrain like this is seen on the Earth or any other planet. We're not sure what caused it, whether what we're seeing are the strong remnants of some erosional process that took away weaker material and formed the valleys between the blades, or whether the blades are crystals that have grown to these enormous heights of hundreds of meters over time, precipitating out of Pluto's atmosphere, perhaps in earlier epochs when there was a more massive atmosphere. This is going to take a lot of study, and I'd be happy to answer questions about it, but frankly, it's just mysterious. This next slide is one of the most interesting things, in my opinion, that we found on the surface of Pluto. It is what looks to the geologists like a shield volcano. In fact, we think we see a number of these, and they're all very fresh appearing with no craters on their flanks. They all have deep, what look like calderas at their center. We have stereo imaging so we can actually measure the depths of the calderas. And the implication is that Pluto has whole districts on its surface that were once volcanic. In fact, evidently pretty recently in Pluto's past. They may even be active from time to time today, just like volcanoes on the Earth. We'll see. We use craters, as I said earlier, to age date the surface. In the upper left here, you can see over 1,200 craters that have been identified by our crater counters. You can see that there are no craters on Sputnik. And even to the east, in East Tombau Regio, there are very few. So, as I said earlier, that's how we know that those are very young terrains. But we can actually age date the different features on Pluto's surface, the northern cratered terrains, Sputnik Planum, East Tombau Regio, the large low reflectivity region we call Cthulhu. And what we find is a wide range of ages on Pluto's surface. Some terrains are 4 billion years old. They're as ancient as the planet. Sputnik is made yesterday geologically, but we also find terrains that are middle-aged. And this tells us, this funny graph on the lower right, on this log-log plot, tells us that Pluto has been active throughout its history. It's not just recently active, but it was active in its youth, it was active in its middle age, and it's active today. It makes new types of geology and new surface units across the entirety of its 4 billion years. Now I want to tell you some things about Pluto's atmosphere, and I'm going to start with this image that was made after flyby looking back that dramatically shows Pluto has an atmosphere. We can measure its temperature and its pressure and so forth with spectra, but we did not expect to see the atmosphere glowing like this, and this is true color, by the way. Pluto's atmosphere actually glows blue because of tiny particulates that we discovered in Pluto's atmosphere, aerosols, that stretch up to 250 kilometers above the surface and which are very finely layered. Here's an image of those haze layers, and you can, if you had more time, you'd be able to count. We count over 24 haze layers, and we see discrete clouds over Pluto's surface. This was completely unexpected and still a bit of a mystery to explain, but that's what nature is doing 4 billion miles away. We can actually use that haze not just to better understand Pluto's atmosphere, but near the day-night terminator, we actually are using the haze to do better mapping because the haze, just like high cirrus clouds on the Earth, reflects sunlight over onto the night side, and when we stretch the images in our computers, like the one on the right, we can actually see onto the night side and map terrains that we never thought we'd be able to image at high resolution. So they turn out to have sort of a bonus for the geologists in addition to puzzles for the atmospheric scientists. These are some results from our radio science occultation by the REX instrument that show in the graph that the upper atmosphere is very similar at different places on the planet where we made measurements, but the lower atmosphere has different temperatures in different places. And counterintuitively, in fact, it's warmest at dawn. And one might have expected it would be coolest at dawn or on the night side, and warmer in the afternoon, but we see just the reverse. So the atmospheric scientists are going to have to explain that. Also, because we discovered that Pluto's atmosphere is colder than had been predicted, it hugs the planet more closely. On the left there is a cartoon version of what we thought Pluto's atmosphere would look like, a big puffy atmosphere around a small planet, before the flyby. What we discovered is on the upper right that Pluto's atmosphere is much more compact and that it's not escaping as rapidly as been thought. In fact, it's escaping only very slowly, just like the Earth's atmosphere, through a mechanism called Jeans escape, which is the same physics that controls the escape of gases from Mars and Venus and Earth and Jupiter. And that was a surprise. I want to close by saying we have many, many data sets that are not on the ground and many types of data from this fantastic flyby. We have color maps and composition maps and stereo maps of the entire encounter hemisphere, and not just the encounter hemisphere for Pluto, but also for Charon and for Nix, and most of those data sets are going to be available before the year is out for the smaller satellites as well. So I'm only showing you the tip of the iceberg, so to speak. the first things that have come to the ground in the first few months after flyby. There's a lot more, and there's more in store for New Horizons because we've already targeted another flyby of a small Kuiper belt object, much, much smaller than Pluto, not 2,400 kilometers across, but more like 24 kilometers across. This is the kind of object that we think the small planets of the Kuiper belt accreted from. And the National Academy of Sciences here in the States specifically directed this mission to do not just a Pluto flyby, but to study one or more of these guys as well. And using the Hubble telescope, we found a number of them. And with NASA's permission, we fired our engines in October and November to target a flyby of this object. It doesn't have a real name yet. It's got a license plate called 2014 MU69. It lies about a billion miles beyond Pluto. And we will fly very, very close to it. In fact, much closer than we flew by Pluto on January the 1st, 2019, in just under 3 years. Now, we have to write a proposal to NASA for the funding of that mission, and we're doing that right now. That proposal is due in April, and NASA will have it peer-reviewed, and if it's highly ranked, then NASA will fund that flight of New Horizons across that next billion miles of space to do that flyby. And I'm very optimistic that that'll get funded, but it's not a done deal yet, so you should know that this is tentative. I'm going to close by going back to Pluto and showing you a video of our highest resolution images as if you were flying over Pluto's surface, beginning at Sputnik Planum and then moving north by northwest across the plane. And I hope this video works for you. Here we go. There's the ice plain with water ice mountains sticking up out of it. We're flying hundreds of miles in just a matter of seconds across the plane to its shoreline. These are what we call the Alidrissi Mountains of Pluto. They're very, very rugged. They're about 4 kilometers high. Then there are badlands further to the west. And then very heavily snow-mantled terrains that we're now flying over where we can look in craters into Pluto's interior and see that dark material. As we get up towards the limb of Pluto, this stops. These terrains are less cratered than other places, and that means that they're younger. Pluto's such a fascinating place. I can tell you as an expert before the flyby that even I didn't expect it to have so much in store for us as it does. But it does. And I'll close by showing you this image again and just pointing out that for my team, this image is kind of the equivalent of the Apollo images of Earthrise over the moon. It meant that the astronauts were really there and could really look back on the home planet and prove that they were orbiting the moon. An image like this can only be obtained by being on the far side of Pluto. And this one was made about an hour and a half after the flyby. And for us, it means a lot, not just scientifically, but it means a lot to us emotionally because we really did it. We really flew all that way across space, across the entirety of our solar system, and explored the last of the classical planets for the first time and excited the world in doing it and made lots of scientific discoveries and made a name for New Horizons. And I want to thank you for inviting me to give this talk. And if you have questions, I have a few minutes that I could answer them.
Excellent.
Wow, that was a lot to say. I hope you have some questions.
Yes, we do have.
I'll drink a little water now.
Okay.
Yeah, Alan, that was a fantastic presentation, and so many thanks. What's the likelihood of the nomenclature being adopted? It seems highly appropriate, and what length of time will it take to get the names in place?
I hope that the nomenclature gets adopted when we submit it. We'll submit it to the International Astronomical Union this summer. Right now, we're a little busy with data analysis and getting the data sent to the ground and writing that extended mission proposal. But we will take care of that errand when things slow down a little bit this summer. I know the names are very popular. In fact, I have people come up after every talk I give, and I've even had people see me wearing a New Horizons shirt and just come up to me on the street, and they don't know I'm the principal investigator of the mission, but they come up to me and say, "Do you work on New Horizons? I love those names on Pluto and Charon. I love all that sci-fi from Star Trek and Star Wars and everything else, and H.P. Lovecraft and so forth." And the fact that the public loves it, I think, is a strike in its favor. I can't give you odds, but I'm pretty optimistic. And thank you for asking.
We have our vote.
That's right. Do any of the results answer the question as to where Pluto was formed in the solar system?
I'm not able to hear that question. Can somebody repeat it more loudly?
Any of the results tell us where Pluto and Charon were formed in the solar system, whether they were an original inner planet?
Well, we know because of the propensity of ices and extremely volatile ices like nitrogen on the surface that they were formed in the outer solar system. Exactly how far back beyond the sun, we don't know. We believe that Pluto was formed about 1 billion miles closer to the sun than it is now, but that's purely based upon dynamical models. It's not based upon data.
Okay. Any other questions?
Alan, even though Charon is in a tidally locked with Pluto, could it provide some of the thermal energy that powers some of the processes in the seas of Pluto?
Again, I'm having a hard time. You're asking about Charon, but I can't follow the question.
Okay. Hold on one second.
Maybe questioner should come up to the microphone.
Hello. Even though Charon is tidally locked with Pluto, could it provide some of the thermal energy that powers the thermal processes in the nitrogen sea?
Well, it may have in the distant past, but currently the two are tidally locked and there's no energy exchange between them. And when we calculate in a computer model how long it takes for a spinning Charon to become tidally locked, it's a very short period of time. It's literally a wink of the eye compared to the age of the system. So we know that they've been in this configuration for a very long time, and that Charon can't be providing that energy source today.
Okay. Thank you. Any other questions?
In the absence of energy from Charon, is there any speculative theories yet about what's providing the energy for all this geological activity?
There's plenty of speculation, and what part of, or whether any of it's right is just unknown. Models of small planets made by geophysicists before the flyby would have predicted that an object the size of Pluto should have cooled off long ago. Just like a small cup of coffee cools off much more quickly than a big vat of coffee, small planets cool off more quickly than big planets because they have more surface area to mass ratio, so they cool efficiently. What's powering Pluto chemically or geologically is really unknown. That's something we're going to have to work on, but I can't give you an answer today.
With the moons, Alan, you say they seem to be composed of pieces stuck together. So is that a similar sort of process to what we see with Comet 67P on the Rosetta probe?
Yes, that's an excellent question, and we've had discussions like that inside our team. That just like 67P looks like a binary merger made out in the Kuiper belt. In fact, that's where 67P was born. The small satellites in the Pluto system appear to be similarly bilobate, and I think they're telling us about the process of formation of the binary and the debris that didn't end up in Pluto or Charon. But we have a lot of work to do to really unravel that story.
Yeah, that's really good. Okay.
Anyone else?
Any more questions? No? No. No more questions.
Well, thank you again.
Well, thank you very much for taking the time to speak to us.
Absolutely. It was a pleasure. Thank you for the invitation, and I hope you have a good rest of your meeting.
Okay, thank you very much.